and gentlemen, how do I start a new model in AnyLogic? Okay, file, new, okay, and I'd like to call this, let's see, I'll tell you what to call it. Environmental contamination hybrid. Okay. This is going to be a hybrid between ABM and SD. Okay. And I'm just going to take us through the sort of very basics of this. So, ladies and gentlemen, we're gonna rip through some initial stages of this to just get some of the basics down, so we can. Okay. Sorry. Okay. So, ladies and gentlemen, this is going to be TAs prepare for deployment. Okay. Okay, we are going to add in a person class, a home class, and a workplace class to this model, and we're going to associate each of them with an icon. For the person, it will be a little person. For the house, it will be for the home, it will be a house, and for the workplace, it will be the thing that looks like a factory. Okay? Okay, and I want to create each of those types first. So how do we add an agent class? Okay, new agent type, and we want to say person. And the person's going to be that person sign, that person thing. We want to add a home. Okay? New agent type, home. We want to add in a workplace. It's going to be workplace. Okay? Okay. Ladies and gentlemen, are we comfortable? Okay. For person, I want to associate them with the little person shape we've been using. Okay? So go down to the pictures area of the palette, right? And drag in the person shape. For home, I want to associate them with the house shape, right? And for workplace, I want to associate them with the factory shape. Are people comfortable with that? I'm trying to secure an economy of scale by doing these all at once, so we can just stay in the palette area and keep on dragging them, right? Okay? Okay, TAs, prepare for deployment. Okay. Was the factory? It's like a factory shape. It's up on the board now. Okay. Okay. Are people ready to go forward? Okay. So, ladies and gentlemen, can we get the lights off in front? Yeah, thanks. Okay. So next, I'd like you to go and I'd like so we can add populations of each of these. Okay. So ladies and gentlemen, we're going to add populations. Where are we going to add populations? Okay, so go to main, go down main, and I'd like you to add in a population of people, of homes, and of workplaces. And the initial sizes of those populations will be given by corresponding parameters. Count people, count homes, count workplaces. Parameters, okay? So we're going to be adding 3 populations, 3 parameters, and we'll make the sizes of those populations dependent upon those parameters. Ladies and gentlemen, riddle me this. What type will those parameters be? an int. They're counts. Good. Okay. So you can watch me if you want to know, need guidance on this. But I'm dragging people over. The population of people will be called populations. The population of homes will be called homes. The population of workplaces will be called workplaces. Okay? Okay? There will be corresponding parameters. For population, the population size will be given by count people. It's going to be an integer. These things are going up on the big screen before you. The population, the count of homes will be called count homes. All of these are integers. The population of workplaces will be called count workplaces. Does this sound a little bit familiar? Okay. Ladies and gentlemen, each of those are integers. The size of the population is given by which parameter? The human population size is given by count people. The home's population size is specified by what? Count homes. The workplace's population size is specified by what? Count workplaces. Who needs TA help? They stand ready. Need some what? I'm going fast. Yeah. I'm doing what might be called informally ripping. Okay, TA? Sorry, W? Yeah. Capital W for count workplaces. Sorry? Yeah, capital W, count workplaces with a capital W? Yep. 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 Count. Yep. Okay. Are people comfortable with this? Okay. I'd like you to build your model. Build early. Build often. And the final. Oh. Okay. I think I should have made this an int. Yeah. Look at that. Oh, that's exciting. Wow. Look at that. Wow, that's wacko. Okay. Okay. Ladies and gentlemen, the final little bit is we're going to have all of these be laid out randomly, and we're not going to need to worry about a dynamic population. So it's a one-time layout. Where do we do that? Okay. Ladies and gentlemen, we're going to have them all laid out randomly. So we go to main. We go down main. And we go to layout type random. Okay? Now, for your simulation here, your default simulation, I would like you to state the following. I would like you for your default simulation to say we're going to have a count of people of 1,200, a count of homes of 400, and a count of workplaces of 20. And I'd like you to run this model and see if you see meaningful results. Okay? You should see something like that. Do you not? Do you see something like this? Something like that? Yeah? Are people okay with that? Okay. Okay, Kurt, Vikram. What were the numbers for these? 1,200 people. Count people is 1,200. Count homes is 400. Count workplaces is 20. Okay. I remember these from the early morning. Okay. While you folks slept, the elves worked. Yeah. Okay. 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 So, ladies and gentlemen, are we okay? Are we in a decent state? Okay. So we're gonna finish just a little bit of functionality, and then we're gonna eat, and then will come the really interesting things. Okay. So a little bit like yesterday. So we're just going to rehearse our mobility familiarity. So ladies and gentlemen, I'd like you to open person. And the people in this model are going to go back and forth between their home and a workplace. So how could we capture that in the model? To go back and forth from a home to a workplace. A state chart. Okay? And we're going to go to a state chart here and drag in a state chart, and it'll be called state chart mobility, okay? And we're going to have one state which will be called off time, and one state that will be called work time. Okay? And there's going to be transitions between them that are triggered merely in this case by time. Oh, I forgot to tell you, we need to set the time unit of this model to be hours. Hours. Okay? So we should go up to the, where do we specify time unit for a model? For the model as a whole, right? And we say hours. Okay? And I'd like, ladies and gentlemen, to go from off time to work will be a timeout of 16 hours, and to go from work time back to off time will be 8 hours. Okay? Sorry? So going from off time to work time will be 16 hours off, and we're going to return to work. So I'll say going to work, and I'll label it, and it'll be 16 hours to go to work. And then from work time to off time will be going home, and it will be a timeout of 8 hours. Okay? So after 16 hours off, they're going to go to work, and 16 hours at work, or 8 hours at work, they're going to go home. And they're going to total up to 24 hours. Does that make sense? Oh, sure. Thank you. Going home, going to work. 8 hours and 16 hours. Okay? Okay? And ladies and gentlemen, we're getting close. We're getting close to the functionality of this morning. And we're getting close to lunch. Okay? Okay. Not just spatial, but temporal proximity. Okay. Okay, ladies and gentlemen, I now want to add. I want to associate. Oh, okay. Raheem, could you go get Merlin? Is Alex going to get him? Oh, okay. Raheem, don't worry. Alex already apparently was dispatched. Okay? Okay. So folks, is it still spinning? Oh, this is grim. So let me ask you Socratic questions. So, ladies and gentlemen, suppose we wanted to associate each person with a home and with a workplace. How could we do that? And suppose we wanted to tell them at the time they're created, to tell them the information on what their home and workplace is. What would we use? Parameter. Parameters do two things. They code the information and they communicate it from the point of creation. So we're going to create two parameters. Is your world still spinning? Okay. Okay. Yeah. Okay. My apologies. Would it be torturous if I added them in front of you, even while you were? Okay. Yeah. Maybe we should do lunch. Although there's gonna be something so beautiful, and it's like 2 minutes from now. Okay. Is Merlin up here? Okay. Folks. So what do we need to add in? Parameters. Okay. So we're going to add in a parameter called home to person. We're going to add in a parameter called workplace. And please tell me, what will the type be of each? For a home, the type will be what? Oh. Okay, and workplace, it's workplace. And what time is it exactly? Could anyone tell me? What time is it? Is it? I thought maybe it was a job that's starting at noon for the network, but it could have been. I bet that's it. I bet there's some big traffic at noon. Okay, still spinning? Oh, the torture. Okay. I think we'd better bake for lunch. So near yet so far. Yeah. It'll tempt you back. Okay, that's great. So to be continued. Our bellies are full, and we're ready for a bit of exercise. Okay, so we stopped with this model that we were building up. And just to recall this, we had a home and a workplace that were parameters for this person. Do you remember this model? So we created, perhaps it's worth reflecting on, we created this model really quickly. And in short order, we created several agent types: workplace, person, and home. And then we added populations of homes, of people, and of workplaces to main, where each such population, ladies and gentlemen, were associated with a population size specified by a parameter, an integer parameter. And then within a given person here, we had defined a state chart, which involved mobility. We classified their time into two components: off time and work time. They would spend 16 hours of off time before going to work. Yeah. Ooh, this is the most uncomfortable fact. Excuse me. 16 hours of work time before going to work. Oh, this is the most terrible thing. Excuse me. Pardon me while I resolve the audio problem. This will be otherwise quite horrendous. Okay. So to recap, we have this model where we've created three agent types: home, person, and workplace. Each of them have been associated with a certain icon. and we had we had introduced into Maine 3 different populations, each whose size was set by these parameters, integer parameters. Within person, we then defined a mobility-related state chart where they would spend 16 hours off before going to work. Hence, it was 16 timeout here. And then they would spend 8 hours at work. And then they'd go home. We further associate a person with a home parameter, which is of type home. I think this is about when your folks' computers exhibited dysfunction. And a workplace parameter, where it's associated with of type workplace, right? Are people comfortable with that? Okay. Anyone have any questions on this piece before we modify it? I want to remind people we have hours as the time unit, right, for the model. Okay, so ladies and gentlemen, I would like you to now set, for going to work, we want them to move to their workplace. How do we do that? Okay, this dot move to, good, and where would they go to? Well, they're moving to what? What does move to need to do its job? It needs what information? 2 pieces of information. An X and Y. Right. So for the workplace, this dot workplace dot get X, this dot workplace dot get Y. Does that make sense? Okay. So I'll put it up on the big screen if you'd like to see it. There we are. I'm saying move myself. This is myself is this. Move myself to the X location of my workplace. My workplace's X value. My, that's this, workplace's X value. Or Y value, excuse me. Does that make sense to people? Are people comfortable with that? Okay. So, ladies and gentlemen, what do you think that we're going to do for the reverse transition, going home? We're going to go home in a similar sort of way, right? Tell me what to type. This dot move to, okay. This dot home dot get X. This dot home dot get Y. Why are you moving instead of jumping? Because you don't want to jump instantaneously home. We're going to move slowly over time. Yeah, we'll see the move. Yeah. Yes. As our LA guest points out, some people would like to teleport to their work. Yes. But given there's more than one home, how do they know which one to go to? We're going to be assigning them. They have only one home, right? They have a home parameter. They have a home parameter, which will be telling them their unique home. We haven't done that yet, though. Well, there's a home parameter with them, right? Right now, you should see a home parameter for the person. Oh no, we haven't assigned it yet. No, we haven't assigned it yet. We're going to. Okay, and finally, folks, when they enter in this mobility state chart, does anyone want me to spend more time here? Okay. Okay, TA? Okay. Okay, and when we enter into the state chart, we want to jump to our home. So we start in our home. When we enter the state chart, so for this entry transition, we're going to do this dot what? Jump to? Yeah. No, because it's just going to be to our home, this dot home dot get x, this dot home dot get y. Okay. So for our entry to the state chart, we're going to jump. So everyone starts at their home, because that's why they're starting in the state off time. Okay? Are people comfortable with that? Are you okay? Who would like me to show this for longer? Oops, sorry. Who would like me to show this for longer here? Yep. Are people comfortable with that? Because it's asking about, you don't actually need it, but it makes it more clear in my view that it's my home, my home's at Y value, my home's, X value, my home's Y value, and I'm moving myself. So rather than sometimes having it, sometimes not, I just thought it's clear to throw it in there. It's very arguable whether it's definitely not needed. It's very arguable whether it adds clarity. I just try to be, if I'm going to do it, sometimes I try to be consistent in always doing it. And even there, I fall short. Are people comfortable with that? Okay, there's a final thing we have to do before we can run this model, and that was mentioned earlier. We have to go up to main and do what? Yeah, give people homes. So where would we do that? Population. And here we're going to assign them a home. How can we pick a randomly chosen home? Homes.random. And then workplaces.random. Oops, no semicolons there. Okay? Are people okay with this? Is that okay? So here, for a given agent, when we're creating that agent, we're going to take the set of all homes, we're going to pick a randomly chosen one with uniform probability. We're going to assign them, we're going to take the set of all workplaces, pick a random one with uniform probability. Does that make sense? Okay. Okay, should we run it? Sorry? Oh, yeah. Yeah, before lunch, we assigned them to a random location. Okay. Do people want to run it now? Merlin, there's been no more problems. Do people want to run it? Okay, shall we run? Okay, where are the people folks here? Where are they? Why are there all those chimneys? Those are actually people's heads. Okay? Here they're going to their work. Oh, look at that. They never even reached their work. They're going a wee bit slow. It sure is interesting. Oh, they're still on their way. Oh, time to go home. Okay, so I see two things that require a wee bit of fixing. Okay, folks, how do we change the order of people so that the people appear in front of the houses rather than appearing merely as a chimney over the roof of the house. Okay, we can click on these icons, and we can click on the top one and say send to back. Okay, now we can click on that one that's still there and say send to back. And there, now we have this one in the front that we want, the one that's a person. Do you see that? Who needs TA help for that? For so we're changing the order here of the icons. Okay, in main. This is in main. Okay, so shall we run it? Okay, TA. Okay, now we have these folks appearing in front, but we still have the commuter problem. Right? Okay. Very good. Okay, so folks, how are we going to change the speed at which they're going? We want to speed them up. How do we do that? Set velocity. So where could we set their velocity? So we set it once, and from then on, it's just going to stay the same. Where could we do that? Yeah, when they enter the state chart, we could set their velocity there. So this dot set velocity, and I want them to cross, let's say, 1,000 pixels. Each of these little squares is 10 pixels. I want them to say, I want them to be able to pass the entire space, which is 500 by 500, within the course of a single hour. So I'm going to set the velocity to be 500 pixels per 1 hour. Okay? That's what we got here. So I'll put this up on the big screen so you folks can all see it. But this is what we've got. Okay. So I'm setting my velocity. For me, set my velocity to 500 pixels per hour. So they could go across the whole length of the space within an hour's commute. I'm sorry? I miss it. Oh my gosh, I am. Thank you. I should have followed my dictum of build early, build often. Okay. Thank you very much. Thank you very much. That's shocking. Computer scientists, maybe someday they'll image a computer scientist's brain. They'll see this big part of this lobe for matching parentheses and brackets and curly braces. Sir, so for myself, set my velocity to 500 pixels per hour of time. Is that helpful? Yes.
Is there any reason why you just don't set it population with the initial velocity?
For the population as a whole?
Yeah.
Remind me, there is a setting in AnyLogic 7 for doing that?
Click on person as initial velocity.
That would be fine as well. Yeah. The question was, is there any reason why not to set it associated with, is it for the population as a whole you're talking, Dale?
Click on person. Yeah, in the
Oh, okay, here. Yeah.
So I guess if you want to have different population.
Initial velocity here. Yeah, sure, I could put 500 divided by that. That's not a bad idea. Sure. Yep, that would be, in fact, I'd favor that. Sure. Okay, any others? Thanks for pointing that out. Any other questions? Are people comfortable? Should we run this thing again? Runner again? Okay, here we go. So ladies and gentlemen, what should we see now? How should it differ? Okay, they all get there pretty quick. Here we go. Boom. You see that? Okay. So we see commuting behavior exhibited. Right? People go home for the night. They come into work.
Some people living in factories.
Well, this is during the day they're in the factories, but then they go home. Oh, you're saying because they're overlapped? You mean like these guys? Well, there's a house behind it. The factory occurs in front. Do you want to make the factory behind the house? Well, then you could reorder it. Sorry? Yeah, well, it's kind of a Towers of Hanoi thing, but yeah, you could do it. You could do it without pulling them apart, but it'll be faster to pull them apart. It's just if you love recursion, you might do it. In any case, okay. So are people comfortable with this? Okay. So, ladies and gentlemen, we're now going to go to a new place here. So you have this model with people going back and forth from work to home and vice versa. We're now going to add something different, okay? We're going to add a state chart for these people, which is going to bring them between a bunch of different infection-related states, okay? Okay, so ladies and gentlemen, we're going to make each person go between susceptible, infected, and recovered states. The kicker, the difference here that we have not seen before is the people are going to get infected from the environment. Pathogens accumulated in the environment. Okay, so think of nosocomial infection, pathogens on surfaces. Think diarrheal diseases, right? Pathogens accumulate in sort of local water. Okay, okay. So, ladies and gentlemen, we want to capture people's progression among 3 stages of infection: susceptible, infected, recovered. How do we do that? State chart. We could, but I don't want to have to open the model up, and it's good to practice these things. Okay? So, and this is going to be a different state chart than we've built before, because we're going to have environmental contamination, not person to person. Okay, so I'd like to have an infection state chart. Okay? The state will be susceptible, infective, and recovered, or it's susceptible, shedding, and recovered. Okay. Okay. Now there's going to be 2 transitions between susceptible and shedding. One of them is going to be a transition that we're going to require someone to start infective. And so that's going to be a message transition. It's going to be initial infection, and it will be just unconditional based on receipt of a message. Secondly, ladies and gentlemen, there's going to be a transition that's going to be a rate transition that is going to be environmental infection. And it's going to be a rate with an initial rate of 0. We're going to come to that in the fullness of time. It's going to be a rate of 0 right now. Yeah, environmental infection. Maybe you should call it infection from environment, but either one is fine. Make it visible. Yeah, thank you. Yeah. Here's initial infection. Here's environmental infection. Gosh, there's got to be a better word for that. What is it? Infection from the environment? Okay, and then there's going to be a recovery transition. And we're going to assume that they remain shedding for a period of 10 days. Okay? Say 7 days. Yes. A message transition, and then a rate transition of 0. A rate of 0 for now, and a message transition that's unconditional. Is that okay? So it's just a message transition, unconditional, and a rate transition of 0. Sure? Yeah. It's just, again, it's just only message. Sorry? The last one is a timeout of 7 days. 7 days. Times day. 7 times day. Yeah. Oh, thank you. Recovery. Okay? And this is a rate of 0, again, initially. It'll be dependent on the level of pathogen load in our environment in a few minutes, but for now it's a rate of 0. Are people okay with this? Okay, so that's good. Ladies and gentlemen, just to make sure this, to help make sure this works and to have a bit of variety in the model, let's add, we want their color to change depending on what state they're in. How do we do that? Add a variable called color, and what's its type? Capital C color, right? And let's go through each of those stages of the state chart. For the first one, the fill color will be green, and we'll be setting the color to what? To green, right? This may seem like old hat to you folks now. Okay, exercise them muscles. Okay, fill color for this is red. Fill color for recovered is yellow. Sorry, gray. Excuse me. Gray with a AY, not a EY. Ladies and gentlemen, what's the final component we need to put in place? Well, who would like me to go over any of those steps again? Yes.
You just show the variables.
Sure. Here's the color variable. It's lowercase color, and it's capital COLOR. Yep. And it's other type because you have to type the name. Okay. Who else needs help here? Who would like me to go over a piece of this? Yes, Trent. Okay. Are people okay? Okay, so folks, you tell me, what's the next step to actually make them change color visually? Yeah, we have to go to the icon. Now, this icon has more texture to it. It's somewhat more articulated process. So what do we have to do? Okay, we have to go person, presentation, person, shape, body. And let's make the fill color color. Is that okay? Is that okay? Are people okay with that? Okay, this is rehearsing the basics. This is like your standard 10 pull-ups with which you begin the day. Okay? Okay? Are people okay with that? Okay. Shape body is accessed over here, Vikram. It has to be accessed through this interface to the left. Okay? Ladies and gentlemen, what do we have to do to start out somebody infective? Infect them. By the way, this is not the only way. Another way we could do is we could have a branch when it comes in, and some of them could start susceptible, some could start infective and shedding, some can start recovered by having a branch here. And that's another easy way to do it. It's harder to control how many start that way, but it's not that bad to do. But we'll send them a message. So where would we send them a message? From whence would we send them a message? From main. And we could, remember, add an event in main. It says initial infection. Remember that? This is a little bit more explicit when you do it this way. Initial infection. And what are we going to do? Just remember, it won't be forever you're at the boot camp. Although it may seem that way. So you'll have to do this on your own. When you're staring at the big blank screen, and I will be far away. So what do we type here to infect? Sorry? Okay, yes, but what's the exact thing? This dot deliver deliver to random agent inside. And I hope that's on my little sheet I've given to you folks. My bequest to you, so that you can help remember without the comfort of me being able to tell you directly. We're going to send the message infect. Now the message, we're going to make that transition regardless. Okay, ladies and gentlemen, that's great. That's great. Ladies and gentlemen, though, how would we're going to want to know if this model is running. How are we going to know if there's someone infected? We can maybe see visually, but maybe they're not obvious. There's so many people around. Maybe one person's on top of another. So how could we get it to report for us the number of people infected right now? Okay, go to stats. Where would we could do stats? Main and population here, all right? Okay. And we can do what? Add statistics. And let's put in a statistic, what? Count infective. Okay. And what's the condition going to be associated with this? Maybe we should say count shedding to be consistent. Count shedding. Just to be consistent in our terminology. And what's the condition going to be? Tell me what to write. Yes, Bahar. Sorry? Oh, thank you. Thanks very much. Okay, what's the condition going to be? What's it going to involve? Look over at that little item. Okay, so it's going to be what? Something like items referring to the person, so it will be item dot. State chart is state active. Infection state chart. The name of the state chart is state active, and this is going to be person dot shedding. That's the name of the state. You don't need a semicolon. This is looking for a value. That's what you want, folks. Okay? Infection state chart. This is the name of your state chart. .isStateActive. Remember, you can fill this out. Maybe some of you called it something different. Use your name. Yeah. Okay. Who needs TA help? We're a lot of the way through this now. A lot of the way through this. Things are getting textured. Okay? Okay, can we run it? Oh, I heard a... Okay, build early, build often. Oh, okay, that's interesting. Let me take a look at that. So where's this? Okay, this is given as the occurrence time. This is the initial infection. You want it to be occurrence time 0. You want it to be in the action. Ladies and gentlemen, for that initial infection, I want to emphasize the initial infection occurs at time 0. It's just the action is deliver to a random agent inside. Yes, Alan.
Two related questions.
Yes.
For that action, could you have sent a message to like a random person? Instead of deliver to random agent, could you have said send message and then in parentheses pick out a random?
Yes, you could.
You could have done that.
Yeah.
And the other question is, do you have to be connected by a network to send a message?
No.
Okay.
No, you don't have to be connected. Just a network would tell you who your neighbors are in a network, and then it's most common to send to them, but you could send to any agent. Yeah. It's not like the network is a necessary conduit. Yeah. Okay, great questions. Other questions? Okay, should we run this thing? How many people will be infected? For now, ladies and gentlemen, 1, for a brief moment in time. So let's pause the model, and here's the count of shedding of 1. And if you look over the model, you might be lucky enough to see the infected person somewhere. But they could be overlapped. There they are. Did you see them? They went to one of these factories down the southwest. Okay, but now they've... Okay. Ladies and gentlemen, are you comfortable with that? So what's the matter, David? Okay, so no one initially starts infected? Okay, scroll down here. Okay, delivered. Okay, so let's go to your state chart. Okay, good. And let's go look at this message. Okay, that's unconditional. That's good. Okay, go look at the statistic. Let's go see the statistic. Maybe there's a problem with the statistic. Where's your... Okay. Shedding. Okay, so you're... Okay, again, show this. Okay, at 0. Okay, scroll up. Show name, yeah. Timeout, once. Okay, go print something here to see if you're getting to that point. Do a trace cell in there. See if you're getting to that point. Okay, I need a TA. TA help needed.
So mine are saying they're mostly red, so I'm not sure where I made that error. I got a lot of it.
Okay, fun. Okay, so he should print something out to see if it gets that place. You got something. Okay, great. So they're all getting red. Okay, can I see your state chart? I hypothesize that the state chart has in it a something which is letting them go from here to here. Okay, that's if the message. Okay, that's fine. Although it should be unconditional. This is a rate of 1. That should be a rate of 0. Okay. Okay, so I need more TAs here. Where are the other TAs? Here, over there.
Fine, it's not working.
Okay.
I have no idea what the problem was.
So, did yours blow up?
Yeah, mine too. My installation is buggy. It keeps blowing up, and this time it actually went off, but I'll find it.
Okay. Okay, who needs professor help?
We're having trouble figuring out why I'm not getting it sounds like a frequent problem.
What's that?
I'm not getting the first shedding.
Okay.
When I run it, I get 0.
Okay. Okay, there's several hypotheses I have. First of all, is this unconditional? I was thinking it might be a problem there. It could alternatively be a problem over in how it's sending the message. So let's go to main, and let's go look at the time that this takes. Okay, this is going off at time 0. Okay, fine. Finally, maybe it's a problem. Could it be a problem with this being non-zero? No. Okay, so that's fine. Okay, so the question in my mind then is the message actually reaching the person? This initial infection, make sure this is going off. Let's do a trace LN and see if it's going off. Sending initial message. Okay, and let's try running it now and just make sure that that's being fired, and then we'll go and we'll figure out who's receiving it. Okay, so it is sending the initial message, so we're in good shape. Okay, so now let's go to person here. Okay, I should check this initial. It is delivered a random agent inside. Okay, let's just go here. Oh, I'm wondering, could they be leaving this state 7 times day? Okay, that's fine. Okay, let's do an action here. Trace LN, I got infected, okay? And infected, okay? And now let's try it. Okay, I got infected. So someone got infected. They must be recovering before you're seeing them. Okay. Okay, here. So I think they're starting infected. Why do you think they're not starting infected? Did you have
Well, when I ran it.
In the statistics?
In the statistics.
Okay, let's go take a look at your statistic. Here's population. Here's the statistic. Okay, that's fine. So let's go now. What time are you looking at it at? Let's stop this time, and now let's click on your count shedding 0. Okay, that's really interesting. Okay, this message did not get absorbed. That's really interesting. So it sent this message and it did not get listened to. So why not?
Who listened?
Well, the people in this state and susceptible. So it's because you oh no. Okay, that's really interesting. So why is it that that's not getting, yes?
I'm trying to random agent, would it be sending to a house or a factory?
That's it. Thank you. Dale got it. Okay, great. Thank you. Okay, yep. Thank you. That is it. Okay, folks, back up for a second. Dale caught an important logical gap that will sometimes get in the way of this model running properly. This is an important difference from with other models, and I'm grateful to Dale for pointing this out. So in main, you recall we had set up this initial infection. This initial infection delivered to random agent inside. That works great for most models we've been working with. What's the problem? There are multiple types of agents. So sometimes it's trying to infect a factory, which is most singularly unfruitful enterprise. So what we're going to do is we're going to use an alternative method to send a message. So this message is going to be sent this.send infect, and we're going to send it to a randomly chosen person. How do we find a randomly chosen person? Population.random. Folks, there we go. That's the fix. That's the rub. So thank you, Dale. That was great. Okay? Okay. So let me go back to that. There we go. I'll put it up in the big screen. Are people okay with this?
Right? Now we have to choose an agent, right? So we want to choose
Sorry? It's sending a message. Sorry? Send, yeah. Yeah. Okay. Are people comfortable with that? Do people want to run it now? Run or not? Run. Okay. Okay. Now we should be able to run it, and it should reliably. It was working a lot of the time before. The problem was that, and part of the issue was there were a lot more people than houses and factories, so it was more likely it was received by a person than a factory. So it would run a lot of the time correctly, but not always. And Dale's suggestion is exactly the right one. Okay, ladies and gentlemen, so who needs TA help still? TAs deploy? Okay, so the question there is your rate transition 0 from the susceptible state?
Yeah, I did.
Okay, it's a rate of 0. Okay, okay, I'm not sure why this is causing a problem. So you don't want that there. You want that up in Maine. You want it associated with this, and you want this like that. That's where you want that. And now you have to make sure it compiles, because right now there's a problem here where it's probably not even listening to it. Where's this G dot? It's test message of.
You didn't put this message.
Oh, okay. It must be something to do with this having something on particular message. You want this unconditional. Yeah. And then here we go. Oh no, this is this one instead. Yeah. First of all, let's build it. Is it happy now? Yeah, it's fine now. Okay. Now let's run it.
Yeah, okay. Never mind.
Okay. There we are.
Yeah, because before that I had all green, all red.
Yeah. There may have been something with that rate transition. Okay. So let's start this again. Oops. Okay. Yeah. There's a. Let's go see how many people are infected. Yeah. There's still one. Okay. Good. You've got it working now. Okay. 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 Who needs TA help here? Okay. We're a lot of the way there, but we still have to put in the crown jewels. Like the environmental accumulation of pathogen. Okay, ladies and gentlemen. Okay, ladies and gentlemen, we are now going to incorporate environmental contamination. We're going to begin with our home. Okay. Ladies and gentlemen, this is in a hybrid section of the week for a good reason. We're going to be incorporating in elements from other methodologies besides agent-based modeling to capture continuous variation in the amount of pathogen present in the home, potentially a reservoir of pathogen which can grow larger or smaller in the home. How can we represent continual build-up and decline, almost in an accumulation? We could do so with system dynamics, stocks and flows. So ladies and gentlemen, I would like you to go to the home, and I'd like you to go to the system dynamics palette into which you dipped in a previous model, and I'd like you to drag in a stock of pathogen reservoir. Okay? And I'd like you to put a flow into that stock and a flow from that stock. This is all associated with home. Each home is going to have a pathogen reservoir. The flow in, from whence does it come? It comes from outside the model. It's just from a cloud. And this is called shedded pathogen, or shed pathogen. Nope, because it's going to be living at home. It won't clash in its names with anything else. You could say shed pathogen at home, but yeah, we're going to be doing the same thing, but they're in different, as we say, namespaces, so they don't conflict at all. You can call something it here and call it over there. They don't fight with each other. Okay, there's another flow that will come out of pathogen reservoir. Whither does that go? It goes out of the model, so we don't have to worry about the details. And this will be called pathogen, die-off? Pathogen, sorry? Inactivation, thank you. Pathogen inactivation. Now, ladies and gentlemen, we see before us a stock and flow model, and I'd like you to tell me, based on our previous experiences with them and based on the lecture I delivered this morning, what must be specified to make this model fully evaluatable, fully executable, fully runnable? We must set the formulas for the rates, good, and what else? Initial value of the reservoir. We're going to make that initial reservoir value 0. We're going to start with a single infected individual, and they'll start shedding, and that will build it up. But we're going to start with no reservoirs of infection. An alternative scenario would be to start with a reservoir of infection, which would be interesting. But here we're going to start with one infective individual, one index infective who might have come in from overseas or what have you. Now, for shed pathogen, well, first we'll deal with the easy one, pathogen inactivation. We're going to put in here a parameter that's mean pathogen lifetime. And perhaps someone from system dynamics area could tell me this formula, well, you could tell me this formula for pathogen inactivation, the formula for that flow, on what must it depend manifestly? The reservoir. It must have been on the size of the reservoir. If there's nothing to drain, there's going to be none per month inactivating. Great, none per day inactivating. And it also depends on the mean pathogen lifetime. If it's a shorter lifetime, more pathogen will be dying out. Will it not? If it's a longer lifetime, less will be dying out for a given reservoir. Okay, so pathogen inactivation, that flow, can anyone tell me what would what would the formula for this be? I'll give you a hint. If we have a stock of pathogen, the units associated with that pathogen reservoir must be pathogen per unit time. Okay? And in this case, our time is in hours, right? Okay? So ladies and gentlemen, mean pathogen lifetime will be specified in hours, and the pathogen, the amount of pathogen will be such and such. What must this formula be? This is a well-known sort of type of formula in system dynamics. If you want to have a mean time in this of a certain variable, what must this formula be? Yeah, there's going to be decay. It's going to involve pathogen reservoir and mean pathogen lifetime. And what's the formulation? Pathogen reservoir divided by mean pathogen lifetime. There's a clear mathematical reason associated with that I don't have time to go into, but you can show in a little mathematical exercise, involves integration by parts. It's a nice little elegant demonstration that if you have this, it's the mean pathogen lifetime. This is the formula. It implies the mean time in this stock of mean pathogen lifetime. So I'm just going to assert that and put in that formula. What that means is if you have a longer lifetime, there's less going to be coming out per unit time for a given level of pathogen reservoir, less coming out because it lasts longer. If you have a shorter lifetime, more it'll be coming out at a faster rate because more of it's dying off for a given level of reservoir. Does that make sense? Are people comfortable with that? So that's how we're capturing decay of this pathogen in situ. I want to emphasize that. This will be an endogenous process. You're going to have this pathogen building up and decaying by itself associated with each home. Now, let us go temporarily put in shed pathogen is 0. Let's build the model to make sure things are fine. Does anyone need TA help? Because now, okay, TA help, front and center. Okay? Okay. Okay? Okay. Folks, what is the mean pathogen lifetime? We're going to set this mean pathogen lifetime to be, well, I'm hesitant to suggest a value. Could anyone suggest a value for a reasonable environmental pathogen? Well, okay. 5 hours? How about something like cholera? Vibrio cholerae. A few days? So you want to say maybe 3 times day as the mean lifetime? 3 times day? We could say something like that. Okay? Okay. It means 3 days? Yeah. Do you want me to help?
No, I didn't specify here what the value is.
Value is 0. No.
So what should that be?
Oh, so there's, is this not connected or is that, no, that's connected, okay. Pathogen reservoir is used but not, is not used but expected. Okay, that's interesting.
Yeah, I got that one too. Or no, has you?
Unless I spelled it wrong.
That's what I'm wondering. Oh yeah, this is not green there. Although no, it is green. It is green. Okay. Okay, pathogen reservoir cannot be resolved to a variable. Okay, let's just try this. Sorry, pathogen reservoir. Okay, yeah, but let's see if it's a happy camper now. Okay, yeah, it's happy now.
All right.
Okay, I don't know what the misspelling was, but there's some. Sorry? Sorry? No, it's when it's infectious. No, it's on a surface. Yeah. For something like Vibrio cholerae, I was thinking, or something like. Yeah. Or in an aqueous context. Okay? So folks, we're a lot of the way done with this, but we have the key piece missing, which is shedding. And I'm going to have to ask for your patience in this regard. Okay. Okay. So folks. We're gonna need to do something conceptually simple here, and we're gonna see how to break it into steps. What we need to do is for each person who's in this home right now, who's infective, we're going to have a certain amount of shedding per hour going on. So we need to take the number of people shedding, number of people who are infected, and multiply it by a shedding rate, a shedding per unit time per person who's infected, to get the shed pathogen here. Okay? So we have to get the count of people that are infected here. And turn that into a shedding rate. Okay? Okay. So, ladies and gentlemen, what I'm going to do is this. I'm going to temporarily assume a really smart person is around. And I'm going to write a formula for shed pathogen here that's going to assume that we already have a function that says count infective persons, and I'm going to give it a list of persons, okay, or count infective, and I'm going to give it a list of persons out of which to count. And the persons I'm going to give it are, now watch this, this dot, it's called agents in range, and the agents, so these are the people who are nearby me, sort of in this home. Which agents do I want to consider? I want to consider people. How do I get a list of all people? Sorry? I didn't hear that? Okay, I want to get actually I have to tell agents range, okay, it's going to find me all agents out of some group called agents who lie within this range. And it's going to be the population. Where does the population live? This .main.population. It lives in Maine. So I have to ask this because it's my population up here. It's my main sort of pointer to Maine. So for my main sort of reference, go get the population, and I'm going to give it a distance of say 10 units. So I could have done less than that. I probably could have done 5 or less, but I'm going to just say 10 units. Sorry? Yeah, yes, I probably could, but I don't want to do it in front of you and be wrong. So, okay, and so waste your time. So I'm just going to do it as 10 now. And besides, I mean, it's not totally unreasonable that if people are really, really crowded together, some of them might have an effect too. So, fair enough. Okay, so it's going to be count infective, and we're going to count the number that are infective in this group, which is going to be all the agents that lie within a range of 10 who are in this population, who are people. Does that make sense? So this is going to give us the set of all people within 10 units of this house, this home, all people within 10 distance units of this home, and I'm going to ask how many of them are infected. Does that make sense? But I'm going... Sorry? It's pixels. It's pixels, yeah. And ladies and gentlemen, and in actually AnyLogic 7, you can get it to be measured in kilometers or whatever if you're using the GIS or meters or what have you. Okay, but ladies and gentlemen, I'm going to do a little thing different. I'm going to ask this thing in Maine. This really smart person who's going to write this is going to be writing it in Maine. And guess who the really smart person is who's going to write it? You. Okay? So you just got to divide this into pieces. You don't want to think of all of it at once. This is the art of sort of breaking things apart into pieces. You have a complex job, you divide and conquer. You figure out how we'll do this part and that part. The first order of business is we want to find people nearby. Having found those people, we want to find the number that are infective. That's how we solve problems. We take them apart into manageable pieces and work on each of those pieces. Does that make sense? Okay. Ladies and gentlemen, so this count infective is not defined. Let's go define it. You notice it says count effective must take a list of persons. We're going to put it in main. Notice what I did there. I put it in main. I referred to it in main. So I said this dot main dot count effective. This dot main dot count effective of this thing. So I'm going to put this thing called count effective in main. Guess what sort of thing that's going to be? It's going to be a function. Okay? It's going to perform a nice job for us. And it's going to be something of which we could be proud. Okay? It's going to be called count effective. And ladies and gentlemen, a function, it does a certain job. In order to do its job, it needs certain information. It's kind of like if you went to the post office and you said, I want to send this letter. They're going to say, well, that's great. You have this envelope here, but we need a stamp on it, and we need an address, and we need a return address. Okay? You give us that information, we'll return it we'll send it for you. It needs certain work to do its job. If you want a contractor to do some renovation work in your home, you have to give them a specification of what you want done. And in return, they will give you something. This count effective, what is it going to give to us back? It's going to give us a count. So that's going to be a what? An int. Okay. And then it needs something to do its job. And this is something that may cause you a measure of discomfort. But it gives us all the hints we need if we look at the problems. We need a count effective that takes, to do its job, it takes a list of people. So we're going to have a list of people, and it's going to be of type list of people. That's what that little begin bracket. This is why I took the vote, whether you people want to do this today. This is the hardest little bit. This is the part that requires the most stamina, the most stick-to-itiveness, the most resolution, the greatest ardency to stick by this. Okay? Here we're going to have a list of people who are going to be taking in, and we're going to go through each of them and figure out if they're infective. And we know how to do that. We know how to do that. We've done this before. It's not too hard. Trust me. Okay. So we're writing this function. I told you someone smart was going to write it, and that person is you. Okay? Sorry? Oh, list of person. I'm sorry. What am I saying? People. List of person. Thank you. List of person. Yes. List of person. Okay, ladies and gentlemen, especially those who have attended the Java tutorials, the proud veterans. How do we go through a list, one by one by one? What do we use? Okay, good. Good, a for statement is right. It's a type of loop. Excellent. Okay, folks? Okay, what are we going to do? We're going to go through this list of people, and tell me roughly what we're going to do. We have this list of people, and what are we going to do? We're going to go through each and do what? See if they're infective, and if they're infected, what are we going to do? We're going to record, oh, there's one more, right? So what we have to do is we have to have a sort of a running count. Does that make sense? A running count of people that we've seen thus far? Okay, watch this. Int running count of infectives, okay? And it's going to start at what? At 0. It's going to start at 0. Eh? Okay.
The option command space doesn't work here.
No. Running, maybe, because it works for me. Okay. Okay? And now, how do we go through each person in the population? We use a for. And remember this? For, particularly those who are at the Java tutorials, what do you do? No, you could do with that, but we actually want to go through each person in this list called people. So what do? If we want to go through each person, P in a list, what do? What's the syntax? It's person P, it's not equal, it's a colon is right. It's a colon. That's what it is. That's what it is. There we go. For each person P. And what do we got to do with that person P? Robin said it earlier. What do we got to do with them? We got to see if they're infective, if they're shedding. If P dot suck it up, soldier. Okay. So if the infection state chart is state active, and person dot shedding. Okay. Wow, that's the worst of it. What do we do if it is active? If they are shedding, what do we do? Maybe we should say count of shedders, right? Instead of infective, just to be consistent. What do we do if it is? We can do plus plus. We just increment it. And then we're basically done. What do we got to return now? Counter shedders, running counter shedders. That's it, folks. What I tell you, a really smart person wrote that function for you. And that person is you. You're to be congratulated. Be congratulated. Now, does this function make sense to you? We take in information that's a list of people, and we have a running count that's 0 initially, because after all, if there's no one there at all, we have 0 shedders. And then we iterate over each of these people, and if they're shedding, we increment that, and at the end, we return that number. So if there was one person infective in here, we're going to be going through one by one, checking. We'll hit 1. It'll be incremented from 0 to what? This we'll take it from 0 to 1. That's what the plus plus means. It just means make this equal to 1 more than it was. A bunch of you saw that before. And then that'll be 1, and we'll continue going through the people, won't find any more, and we'll go and return that value. If there's 2 people, we'll go through, start at 0, go through, we'll go from 0 to 1, go through more, go from 1 to 2, and then return it. Are people? Yeah, question. Yeah. Yeah. This is all the people that we need. And before we were always counting it in the whole population, but here we're being told, hey, count the number infective in this set of people. Okay? Why is it different from the population? Because here we're asking all the people in a home that are infected. So we're going to be, it's a subset of the population. I'll go and show this where this is used, okay? And maybe it'll help to name it this. Ladies and gentlemen, to be careful here, and to help reduce confusion, I'm going to call this count infective in a group, okay, or in location, in group. It's a group of people we're specifying. Count infective in group, okay, and I'm going to be specifying this group, and I'll call this my group, and I'll go through each of them in the group, okay. And where does this group come from? Why are we defining this function? Because it's going to serve for us in 2 places. It's going to allow us to count the number that are infected in our factory, in our workplace, and the number that are infected in our home. Where are we using this, folks? Do you remember where we were using this? It's in that darn flow. It's in that flow. So let's go to home here, and it's right here, folks. It's right here that we were using this. We're doing count infective in group, and we're counting the number of all the agents that are nearby us. In other words, within this home, how many of them are infected. It's not in the whole population. It's the number who are here in the home. Count infective in group. And it's of these agents in the home. That's what this is. Agents in range. The agents within 10 units of this. Yes, Alan.
How do you know that agents in range gives you a list? And what is that list? Is it an array list? Is that a AnyLogic thing?
Just do this for it. So, control space. It gives us a list of agents who lie within a certain range. Yeah. So Tiffany, does that make sense to you? Yeah. So the idea here is that we're asking, count the number of infective agents here within this home. That's what we want to do, and we're going to multiply it by some shedding rate, and that is going to give us how much pathogen is coming in here. So, yes? Well, that's what, there's a final coefficient I'm going to be putting in. Yeah. So there's a coefficient, a shedding coefficient. Okay?
Can you just go back to your function and your flow spectrum changes you made there?
I'm sorry?
The function and the flow. Will you change it to group? I made an error there.
Okay. I changed it to group, and I put it in group here. Yeah? That's it?
Change that, so that's P, so we're now calling it group, right?
So you've got a capital G group. Did you call it capital G up there? Or up further up? Do arguments? Argument?
Oh, I didn't change that.
Yeah, you need to
change that to group,
yeah. Right. Okay, folks, who needs help here? Yes.
When I added a group,
Yeah.
it doesn't like it.
You have to change this to group.
Oh, this?
Yeah. Yeah, that has to be group. Yeah. Okay, ladies and gentlemen. Who needs me to show something on the screen here? Okay. Ladies and gentlemen, we're just about done with this piece of it. But there's one final parameter we need to add. Yeah, but I'm not done with it. I'm about to change it. So here we're going to add in, ladies and gentlemen, we're going to be adding in a parameter called shedding, per capita shedding rate. Per capita shedding rate. That's going to be the amount that each person sheds. And we're going to connect a link between it and this shed pathogen, okay? There we go. And shed pathogen, Priyasri, this flow, we're going to have a per capita shedding rate times that. That's what we're going to have. And per capita shedding rate right now is going to be, well, I don't have a particularly strong value to use for it, so I'm going to say it's 1.0. It's about basically the rate with which pathogen accumulates per hour from a given shedding person. And I'm going to say it's 1 unit of pathogen per shedding person. We can pick our units of pathogen. Okay. So ladies and gentlemen, we now have a pathogen reservoir building up. in the home. It's from shed pathogen. It says per capita shedding rate times the count infective in group of this group, which is the set of all agents within this distance of me. Sorry? 1.0. No, it's that per capita shedding rate times it. Times that thing. Yeah, all we did, folks, is we put this thing times this. No, 1.0. Yeah. No, it's a double precision. It's a 1.0. So it's not 1. It's 1.0. Yeah.
So I'm not sure I understand what the double is.
It's a floating point number. It's like a 2.3 or 4.2 or as opposed to 1, 2, 3, 4, 5. Yeah.
Why would you say 1.0 is default? Why not?
It's a double precision value. I wanted to communicate that it's a double precision value, but 1 would do fine.
Oh, God, sorry. I thought you were racist.
No, it's double.
Ah, thank you.
Yeah. Okay, folks. Put what on the screen? This one? Yeah. All this is all I did is I put this in front of it. Okay, this is what was there before. It's the same thing that's been there all along. Well, I haven't changed any of this. All I did is I put this in front of it. The per capita shedding rate times it. Okay? Yes.
What would you suggest if a model hits play and the time doesn't advance anywhere? I've been looking for infinite loops. I've been looking for weird message delivery cycles. I'm not seeing anything.
For which one?
David's right here. We're doing this exact same model. It's just
David?
yeah. So we're hitting play on it.
Okay.
And the runtime is 0, and it
Okay.
can just sit there. Nothing.
Well, I would make a copy of the model. I would rip out pieces of this and see if it advances then.
That, actually.
Yeah.
It doesn't really make much of a difference. Maybe it's an AnyLogic thing. Well, try turning it off.
I wouldn't think that's it. I think it's likely to be, I would rip out portions of it. So, yeah. Yeah. So when did that start happening? When we're doing the function. Okay, so I would get rid of the function. Maybe it's got an infinite loop in the function. Okay. Okay, make the function return 0. Yeah.
And that's just when I try to run it, even though it's on the build, there's no errors.
For shed pathogen. Okay. Shed pathogen. Okay, here we go. Oh, yeah, yeah. Oh, yeah. Maybe it's because you have a semicolon at the end. No, count infection group. Undefined for type main. Okay, count infection group. The other doesn't look bad. Count. This is called count infective, so you have to do it count. Count infective in group. Okay, you're fine now. Yeah. Yeah. Okay. Oh, that's interesting. It's still exhibiting that. So Dylan, I've got the same problem here.
We're starting to think that I don't know whether when we put shatters, I think whenever we put shatters anywhere at the
Sorry. So, okay. So I'm gonna put in here temporarily this, and I'm gonna see if it works then. Okay, are other TAs circulating? We need all TAs here. Priyasri, could you go get Winchell also? I think we need all TAs because there may be other people needing help. So who needs help here? Are you getting any errors at all? Okay. So double in. Okay. Oh, return 0.0. Okay. Yeah. Fine. Okay. Yeah, I've got an idea what it is actually. So Dylan, I think I know what it is. Yeah. Okay. I think I've got it. Okay, folks. I think we're going to need to reduce the population size. I think that's probably a lot of the issue. Either that, or we need to change parameters for the simulation. So let's try this. I'd like you to create an alternative experiment where we have a much smaller population, and we'll test it with that. Dylan, yep. Try this. So create an experiment with, it'll call small population, and make it a population of 10 people and 1 home, or say 2 homes, and 1 workplace. Okay. So try that. Did you try a new experiment?
We're getting to it.
Okay. Yeah, finish. Yeah.
Oh, I just need to put different.
Yeah. So you want 10 people, 2 homes, 1 workplace. Yeah. Oh, yeah. Okay. So we want to run this. Yep, it's working. Okay, good.
So it looks like getting all the nearby agents is a really inefficient thing in AnyLogic.
Yeah, I think so.
But where is the 10 people?
The 10 people are here. So 10 people are.
Oh, okay. So
yep, they're in the homes. Yeah. They're in 2 homes. Yeah. Yeah. Okay, folks. So were you able to do that?
Yeah, that works. Yeah, cool.
Okay, folks. So for some of you, you may find the model is slow, in which case I would suggest simulating it with a very small population, specifically, say, 10 people, 2 homes, and 1 workplace at first, just to make sure it works. Okay, and you should see something like this. So, George, yeah?
that thought, I guess I'm still not clear on how you're connecting your stock and flow model back to those red and green states.
Right.
That we still don't have anybody connected to that.
Correct. That's the final step we're going to be doing right now. That's the final piece that remains is going to connect them, although we have to do something similar to what we did for a home for a workplace. But that will be a matter of simple cut and paste for the most part. Okay? Okay. Okay, folks, so who needs TA help now? TA help? Okay. So ladies and gentlemen, I'd like you to go to home, and I'd like you to take a copy of this stock and flow. So, ladies and gentlemen, go to home, take a copy of the stock and flow, and I'd like you to copy that into the workplace. Let me state that again. Go to the home, take a complete copy of the stock and flow diagram, including those parameters, and I'd like you to go place it into the workplace and paste it into the workplace. Okay? And now there's only one difference. After you've pasted it in, go to shed pathogen, and for that formula, no, in fact, there's no difference. No, it can all be used directly. Okay, we're fine. So now, build that model and try running it again. And I'd like to show you what's going on. We have two homes here. Ooh. Ooh. Okay, that's interesting. That's interesting. Okay. Here's the population members. They look okay. And here we have workplaces. Okay. Indeed. Looks like maybe I said it. Oh, visible. Sorry, folks. I made it invisible, it looks like. So in both in yours, it's probably visible. Visible. Okay, so I'm going to run this again. So what we have here is we have a single index infective, and they're circulating in this population. And initially, they're in their home. Home 0 is 0 pathogen. Home 1 has some pathogen built up. Why is this pathogen building up in that home? That's where that sentinel case lives. And over time, what's going to happen? That sentinel case is going to move over to work.
How did you find that one? Oh, you went to one.
I just scrolled through here and found the one that had it. I knew there had to be one that had it. Okay, now they've gone to a workplace. It's time. They've been at a workplace. Let's go see the workplace. Here's a workplace. You notice the workplace is now decreasing. Why is that? Can anyone say? Here's a graph for the workplace. It's decaying now in the workplace. Oh, now it's going up. Why do you think that is? Back to work. Back to shedding. It's going up. It's going down. Well, where are they? Well, it's going down. They're at their home. Let's go check out their home. Here's their home. Oh, sorry. Here's their home. Let's go check out its trajectory over time. This is what we see for it. It's been rising up and then decaying. Why is it decaying? They're gone at work. And now why do you think it keeps on decaying? They've gotten better.
So if you're not seeing anything change, is that because something's wrong or it's just slow or?
I think something's wrong. So, but check the different.
There's only one, right? There's only one home.
There were 2 homes, right? I thought there were supposed to be 2 homes.
2 homes, yeah. There's 2 homes.
Yeah.
Yeah, 1 workplace.
Okay. So run it. Yeah. So let's go see. Let's go see population there. Okay. There's no shedders right now. So somehow you don't have a person infected.
It's not firing, so it's not doing that first infection.
Evidently not. So let's go to main. Let's go to the initial infective.
Okay, so how do I get back?
Okay, in fact, population not random. Okay, so are they getting infective? That's what I want to know.
So would this?
So first of all, check that rate there. No, the rate to the right. No, that's 0. Okay, good. And okay, you don't want it on text because we're not sending them text. Unconditional. Yeah. Okay. Now you should see that. Yeah. So some people were having receiving a specific message. We can just do it unconditionally on the message. Okay? Okay, folks, are you seeing this as well? Okay, are you seeing that? Okay. We're going to have a final step. I wanted to remind you we put it into workplaces and we put it into home, this representation. The final component is what? Yeah, getting the person infected based on that exposure. So, ladies and gentlemen, I'm going to ask you to steel yourself one more time. Okay? Okay. We're going to fill in this environmental infection. But before we do that, I'm having an internal heavyweight battle I am having an extremely strong feeling of cognitive dissonance. My software engineering professor side is beating up on my modeling professor side, and there's a real tussle. Should I do it in a way that's a little bit easier for you, but not fully proper, or should I, and it's quick, but it's much better to do it another way, or should I have you build another function? It's really difficult. It's really difficult. Beauty and efficiency are banging each other. You want to do it the quick way? The new generation. Okay, beauty. Okay, thank you. Okay, ladies and gentlemen, go to the general palette. I stand reassured of the new generation. Okay, this won't be that bad, folks. It won't be that inefficient. Drag in a function. This is going to be beautiful. Drag in a function from the general palette and call it current exposure level. It's called current exposure level. Okay? Okay. This is going to be the current level to which they're exposed. It's the amount of pathogen. It's going to return a double. It's going to return a value that's a double, okay? And it's going to be their current exposure, how much they're currently getting. And what is that going to be based on? They have an infected workplace, an infected home. What's going to be their current exposure level? Based on where they're currently at. How would we know where they're currently at? Looking at the information here, how do we know where they're currently at where they're currently located? State chart. Okay, I'm going to abstract over the fact that they're traveling. We can put in an in-transit state, but I'm not going to do that. Okay. Okay, so this is what we're going to do. We're going to say if this dot state chart mobility dot is state active work time, person.work time, if there this work time state, and we always put this person dot in front of it, if that's where they are, ladies and gentlemen, if they're at work, what is it that's going to determine their level of exposure right now? If they're currently at work, if they're in this work state, what is it that's going to be their exposure level? We would look to their what? In the workplace. In their workplace, what's the pathogen reservoir, right? So their current exposure level would be, okay, if they're at work, are they getting exposed at home? No. What's going to be determining their exposure level if they're at work? What's the pathogen reservoir at their workplace, right? So if they're at work, we're going to return this dot workplace dot what? Pathogen reservoir. Does that make sense? Otherwise, if they're at home, what do we return? This dot home dot pathogen reservoir. They're at home. We'll return the amount of reservoir pathogen that's around at home. If they're at work, we'll return the amount that's at work. Does that make sense? That's their current exposure. Does that make sense? Okay. The beauty is almost complete. Okay. Ladies and gentlemen, we're going to drag in a parameter, which is going to be what do I call it? Infection hazard per unit exposure. Oh, something like that. Okay? Okay. Infection hazard per unit exposure. It's how much chance there is per unit time of getting infected per unit of exposure to which they're currently exposed. And guess what the rate of infection is going to be? This rate, this per hour rate of infection is going to be based on what? It's going to be the infection hazard per unit exposure times the current exposure level. Have you ever seen something more beautiful than that? Infection hazard per unit exposure times the current exposure level. If they're being exposed not at all to zero, they're going to have zero chance of being infected per unit time. If they have a current exposure level is 100 levels of pathogen, we're going to multiply it times this per unit of pathogen exposure to get their current chance per hour of getting infected. Now, in general, we would have a dose-response relationship that would relate their chance per hour of infection based on the related exposure level. We're just going to multiply the two here. Okay, and now we need to set an infection hazard per unit exposure, and we're going to set it to be 0.1. Okay, this infection hazard per unit exposure. And ladies and gentlemen, that's it. We are complete. The job is done. The model will run. Well, at least my model will run. Okay, who needs TA help? Okay. Okay.
Love it. I don't know what's happening, but it's working.
Okay, folks. Okay, let's run this thing. Let's run her. Look at that. Oh, man, look at that. Look at that. Okay, here are their homes. Look at this home. This home is rising pathogen levels. How about this other home? This other home has rising pathogen levels. What does that suggest?
Oh, people visiting each other.
People are, well, they're, okay, the workplace number 0, workplace number 1, workplace number, oh, there's only one workplace. Okay, ladies and gentlemen, we seem to be cooking with gas here. Okay. Okay, ladies and gentlemen. Okay, this is great. Beauty has triumphed. The younger generation, has seen it. Okay, ladies and gentlemen, I'm going to actually just put in something to make it a little bit clearer visually about what's going on. We're going to put in a little rectangle next to each little thing for the factory and for the home. And that rectangle will be colored according to the pathogen load at that factory or at that home. Can we see that? Okay, ladies and gentlemen, shall we compute?
Yep.
Okay, so I just dragged in a rectangle to home to put it next to the home. And I'm going to have the color of this rectangle be set by the pathogen level. Okay? So next to the home, I dragged in this rectangle, and we're going to give a formula for it that's LERP color, pathogen reservoir, divided by 200.0. Yeah? And then we're going to put in, it's going to go from white to red. In other words, the closer it comes to 200 or above, it'll become totally red. Below that, it'll be totally white at 0. Version 6 it was in. Yep. Okay? Folks, we just put in this rectangle here into home to color it according to how infected it is. So we're going to be able to see visually with every home how badly infected it is. Okay? What's that?
Bring out your dad and
Okay, a question up here front. Okay, ladies and gentlemen, and I want you to take that same rectangle and copy and paste it into the workplace. Copy and paste it into the workplace. Put it up next to the factory. Okay? Build early, build often. And as far as I'm concerned, this model is complete. I'm going to run it now. Look what's happening, folks. Look at my computer. What's going on? Can anyone narrate what's going on here? Yeah. Ladies and gentlemen? Yeah. So here, I'll put it up here on the big screen. So ladies and gentlemen, I inserted next to each factory and home image, I inserted a rectangle and made its fill color this. There you go. Yes. Yes.
And it runs just fine.
Yeah.
You don't know, so there's a total number of 10 people in this model, right? So, and because they're moving together, this house could have 10 people, or this house,
Right.
well, this house could have 9 people, this house
Right.
could have 1, this
Right.
could have 3 and 7.
Right.
But in the number of people per house,
Yeah, we could. Okay, yeah, here. So, okay, there's a good question here. We stuck 10 people into 2 houses here. Let's go create a somewhat bigger population where this can be seen. So we're going to create a new experiment, and this is going to be called medium population. Medium population. Maybe I'll call it medium small. Medium small population. And this will consist of maybe 100 people. They'll be into maybe 30 homes, and there'll be 5 workplaces. 30 homes and 5 workplaces.
How many people did you say there were?
100 people. 100 people, 30 homes, 5 workplaces. This is the very height of the boot camp experience, in the sense of this is as intense as it gets. And I realize this is really pushing your limits. But you can watch as this plays out. Yes?
no, so the question is because these agents are
on top of you. But I'm spreading them. The problem was there were so many in a home that they were really...
So is it, well, but now, so the question is, some houses have 10 people, some houses have 50 people, some houses like some houses might have, how do you know how many people, so that's 100 people spread out over 30 houses, right?
100 over 30, yeah. So
but how do you know how many people per house there?
you could make the house size depending on the number of people, and that would show it. Yeah?
Okay, because that intensity then fractions.
That's right. That's right. Yeah, it's a good point. So, folks, there was a question from the group. How would we show it so the size of a house, how would we show visually that a certain house has more people in it? How could we do that? We could make it size depending on the number of people that are currently in it. Something like that. Do you want to do that? Okay. Okay. Wow, I thought you folks were totally burnt out. What is it they say? Feel the burn? Okay, so folks, let's go set it so that for the home, we'll set it so the scale of the house is dependent on the number of people there. Okay? Now, ladies and gentlemen, I'm having cognitive dissonance. There's 2 parts of me that are fighting. The efficiency and the beauty. Beauty. Okay, we're going to create a function called getScale. And then instead of repeating the same horrible formula for each of these and cutting and pasting it, we're going to call the function called getScale. Okay? This is going to be a beauty. Okay, we're going to drag into home a function. And it's going to be called getScale. It's going to be the scale of that function. What scale to show this at. Or better yet, okay, no. Okay, oh gosh.
Yeah, come on, do it.
Okay, oh gosh. Add another function called occupant count. Get occupant count. Okay, what is that going to return? It's going to return a count, and therefore it returns a what? An integer. Okay. And how do we determine the number of people here? You tell me. How do we determine the number of people in this home right now? We did it before, folks. We can do it again. We did it before. What do we do? Okay, that's a great start. Agents, that's good. That's a great start. This start, agents and range, we're going to ask all those within 10 units, and we're going to, and what agents do we want to consider? Do we want to consider a factory as an occupant of a house? Most certainly not. We want to ask of all people in the what? In the population. This dot main dot population. We're finding all the agents in range from the population, in other words, the people, and we want to ask how many of them there are. So we'd call size on that. Oh, a thing of beauty. Look at that. Look at that. We return size, the size of this count of population. So find all of people in range who are from all the people in 10 units. In other words, the count of people in the population who lie within 10 units of us. That's going to give us a list of people, and we ask for the size of that list. Boom, done. Okay, now get scale. So this returns an int. It returns an int. This is the natural way you decompose problems. This is what, I know you probably think this is why we're so strange, but this is how we spend our days, is figuring out how to take a problem, take it apart into manageable pieces, and have each solution to those pieces. And often it involves suspending your disbelief for a certain amount of time, saying, there's this really hard part that I'll get to later. I'm going to put it aside right now and focus on the other parts, and I'll come to that part later.
The clever art of procrastination.
Yeah, it's keeping yourself motivated. So get scale here will be get occupant count. This dot get occupant count times I don't know. Maybe we'll take the log of it. Log of it plus 1. Log of it plus 1.0. So it'll never be plus because that means if there's 0 people in it, its size will be 0. So maybe I'll add 1 to it. Yeah.
Should that be returned?
Should be returned?
Should you be returning that?
Yeah, returning it. Thank you. Return that thing. Okay, this is what I did. So I said, how many people are there in this house? I'm going to add it to 1 because if there's 0 people, I don't want log to have a problem. So I have this get occupant count plus 1, and I'm returning a scale, so it should always be at least 1, and sometimes it'll be larger than that according to this. Oh, that's a thing of yeah, it returns a value. It double. It returns a value double. Thank you. And this is the formula for it. Oh, this is beautiful. I can't believe you're letting me do such beautiful things.
You know, you sound like Jimmy Stewart when you really get into this.
Who's Jimmy Stewart?
Oh, you're not old enough to yet.
Okay.
You talk to a big rabbit.
Okay.
A function called Get Hardy.
Oh gosh, okay, folks, we need to call this something else. We need to call it get visual scale. Sorry. It's exhibiting dysfunction. Get visual scale. Okay? Okay. It just clashed with something that was already there I didn't know about. Okay, it's returning double. I just renamed it. Get visual scale. And this is what it returns. I take the occupant count, and I want to deal with the fact I don't want it to blow up if it's 0, so I add 1 to it, because log of 0 would cause big problems. So I add 1 to it, and then I add 1 because this is going to be a scale. A scale is sort of relative. 1 would be the normal size of the house. 2 would be twice the normal size. 3 would be 3 times the normal size. And so I want it to be at least 1. Okay? Okay. Oh, okay. Wow. Well, wasn't that something? Okay, and then how do we make this actually the scale of it? How do we make it the scale of it? We do it up here in the house. We make it get visual scale. For the scale X, scale Y, scale Z. There we go. Okay? That's an answer to Chris's request. Yeah. All I did is I went up to the house and I went to its scale X, scale Y, scale Z. And I just called that. Instead of having that horrible formula.
When they leave the house, they shrink back down to their size.
Sorry, when they leave the house shrinks. Yeah. Yeah, because no one's there anymore. And then we could do the same thing, ladies and gentlemen. I mean, you could do the same thing and for the factory, right?
You just cut and paste.
Yeah, you just cut and paste, and you could do the same thing for the factory. Folks, do you want to see it for the factory? Just cut and paste it into the factory and then make the factory size depend on it, right? Okay, watch this. There's going to be pulsing houses, right? Well, that's what Chris was asking. How do we know?
Well, I didn't ask the pulsing house. No, just to know, like, so, I mean, one reason is to know how many people per house, so that's what that means.
Indeed. Yeah. Well, then we'd have to kind of remember how many people are permanently assigned to that house. And so what we could do is when they first enter that transition state chart, we could say increase the occupancy of the house, and each house would maintain a count of number of people that are the permanent occupants, and you could increase it for each person as they enter the state chart, increase their associated house, and then the house would stay permanently if that size. But I think this has a certain kinetic art quality to it. Doesn't it? I mean, it's kind of evocative, and you can have the factories grow as well, and if you wanted to. But okay, so what we can see here is that certain houses are lower burden houses than others. Certain have quite high burden of infection, right? And the factories seem in general to have a very high burden, reflecting the fact that they have large populations. Okay, now ladies and gentlemen, what do you think is going to happen over time here? Well, is it going to explode? What's going to happen? Oh. Okay. Okay. So what's happening over time? Let's go down to the factories. And let's go plot out what's going on. Why is it decreasing? Well, everyone's recovered now. Everyone's recovered. So ladies and gentlemen, I don't want to distract. So there's a lot of mechanism that went on here, and I'm really floored by how tolerant you've been for me, because I've taken you on a pretty challenging journey, and that is the most challenging and arduous component of this boot camp you've just been through. And I'm amazed that you've been able to tolerate it. But we shouldn't lose track of the big picture of what's gone on. The big picture is that we've been able to use hybrid modeling in the form of agent-based modeling on the one hand, with these different types of agents, people and their workplaces and homes. We've combined that in quite surgical ways with system dynamics modeling by building up pathogen and decaying pathogen so that we can capture over time the buildup and decay of pathogen across the population. What that means is every place in the population, all the homes and all the workplaces, are each associated with endogenous dynamics associated with pathogen buildup from exposed individuals and associated with pathogen die-down due to inactivation in the environment. That's of significance. We hadn't previously seen this sort of environmental contamination. We hadn't previously been privy to sort of how we can characterize dynamics associated with places. And now if we went in, we looked at the workplaces here, for example, we could find that, over time they're evolving and they exhibit this kind of natural dynamics that's described crisply by these stocks and flows. And if you think about it, we can very comfortably use state charts to capture transition between discrete states. But really, stocks and flows excel in capturing continuous dynamics, things like changes in weight over time, changes associated with blood sugar levels, changes associated with levels of concern, or buildup of pathogen in a certain circumstance. So here we've been able to put together a model where we can capture environmental sources of pathogen or environmental reservoirs of pathogen and capture their natural dynamics in a fashion that's coupled with the dynamics of infection in individuals in the underlying population, these particular individuals who are circulating through the population. It's of note, and here we basically have ABM inside, or SD inside of agents. System dynamics is working inside of agents. Before we had SD producing agents. Now we have SD inside of agents. And in the final little bit here, I'm just going to show you a glimpse of a model. We're not going to, well, gosh, let's do it here. Let's do it here. Let's do it here. Let's just show, we could show it in less than 5 minutes, how you can use SD at a high level to summarize things at the agent level across the entire population. Okay, so ladies and gentlemen, let's finish this model. We're going to create a stock. We're going to create a stock at the high level of pathogen levels that's aggregated across agents. And you're going to tell me how to do it, because we know how to do it now. So ladies and gentlemen, suppose I wanted to, in this model, I want to compute the total of the pathogen reservoirs across all workplaces. How would I do that? I want to compute a total of pathogen reservoir levels across all workplaces. In other words, I want to sum them up to get one number. Okay, we want to, so we have some number of pathogen workplaces. Some will have higher levels, some we have lower, and we want to sum them all up. So at any one time, we could see the total amount of pathogen in workplaces. How would I do that? Okay, I could do a function with a loop. That's one way to do it, and I don't deny that.
Or could you go to you can go to main and get it from home and factory.
Okay, I'm hearing, we've done it before. Remember when we needed to do a plot and we wanted to plot out the count of people infected? It is something, doesn't go by the name data, it goes by the name statistics. Let's go to the population. Remember, we could associate it with workplaces, and we could define a what? A statistic. We could sum up, right? Across this level, we could sum up the pathogen reservoirs, right? Pathogen reservoirs at workplaces, right? Right? Workplace pathogens. We could sum up the, you tell me, home pathogens. What, ladies and gentlemen, what should I put here? If I want to sum up the home pathogens, what should I put? What should I put? If I want to sum up the pathogens across homes, what do? Do I take a min, a max, a sum, and what do I put for the expression? Oh, gosh. Oh my gosh, thank you. Okay, yeah, let's go to homes. Sorry, add statistics. What am I doing? So this will be home pathogens, and what should this be? It should be a sum of what expression? Item is the name of the home, dot, what? How do I tell how much pathogen a home has? Pathogen reservoir. Pathogen reservoir. Right? Could I do that? Is that okay? Okay, ladies and gentlemen, do you want to create a graph for me of the pathogens? Sorry? Oh, yeah. Do you want to should I create a graph of the amount of pathogens in the homes and in the workplaces? What do you think about that? Yeah? Okay, where would I create a graph from? From whence would I create it? From whence would I create a graph? Analysis. Analysis palette. And I do a time plot. Okay? Do a time plot. And what were the two things that I'd plot out? Okay, good. So I put a time plot, and where do I add something to be plotted? Pathogen levels. What's that? Add data item. Okay. And this will be maybe a workplace pathogen. And how would I calculate that? What would I say? Ladies and gentlemen? This dot, what would I ask for its? Okay, I'm going to ask, where is the statistic living? It's in? Yeah, it is, but so is his time plot. So we say this means main, dot what? Workplace says, exactly, dot, and it's the statistic we just defined. So what is it? What do we call it? Workplace pathogens? Whatever you called it. And then similarly, I'm going to have a home pathogen. And that's going to be, what would I type here? This dot what? This dot homes dot home pathogen. Maybe I don't need to say it all. It's kind of wordy to put home pathogens if it's already in homes, but it works. Okay, can we plot those? I'll put them up there. I'm sorry, I didn't mean to. There we are. This dot workplace to workplace pathogen. Just use autocomplete. Don't try to type things, folks. We try to avoid typing things if we can because we make spelling mistakes and so on. We do autocomplete, control space. The time is long past where I, as a young man, had to keep the names and the definitions and the order of the parameters of all these hundreds of functions in my head only. Now it can help us type them out. Okay? Are people comfortable with that? Should we plot it? What do you think? Okay. Okay, here are our graphs. Look at that. Why are they only in homes right now? Well, because no one has gone to the workplace. Here comes home pathogens or workplace pathogens. It's died down some. Okay. Okay. Who needs TA help? TA help? Ladies and gentlemen, we could see that the epidemic remains spreading. Okay? Great. Great. It's quite an interesting little graph, too. But it is reflective of the fact people spend more time at home than at workplace. Okay, so the final thing we're going to do is we're going to put in place that element. We're going to add a stock and flow at the highest level to total things up across the population. Okay? So we're going to total up in the stock and flow area here. From the stock and flow, we're going to add a stock, which is going to be cumulative infection days of people. And we're going to have a flow into it, which is going to be called new infection days. Cumulative infection days is going to start at 0. In new infection days, ladies and gentlemen, it's just going to total up this dot population. Where can we get the total count of infectives? You know, I'm thinking to avoid, to sort of lessen the, well, no, it's not bad, okay. Dot count shedding. We can get the number of people that are shedding, and that will give us, if we total it up over time, we put it as a flow into here, it will give us cumulative infection hours. So what we want to do is, we want to essentially take the number of hours per day and divide by it. So hours per day. So it would be divided by 24, for example. Or better yet, multiply times hour divided by day. Or divide by hour per day. Yeah, that's what we want. Okay, that's cumulative infection days. Okay. Maybe we'll change that just to be more transparent to cumulative infection hours, just so it's not so confusing to people. Cumulative infection hours, and we can later divide it after it's totaled up. So this is what it is. Cumulative infection hours is exactly that. We total up the number of infection hours over time. Time is measured in hours, so it's cumulative infection hours. Okay? Okay. There we go. So if we wanted to plot cumulative infection hours, we could do so directly interactively. So here we have a stock that's accumulating over time. So here's the stock at a high level, summarizing across the population. And we could create similar stocks for pathogen, cumulative pathogen levels, quality adjusted life years lived, cost, etc. I won't go into those, we don't have time, and I'd like to switch to project work. But this totals up quantities across the entire population. Yes? Yeah. So cumulative infection hours just was 0 initially. And new infection hours was the count of people who are shedding. A certain number that are in shedding and integrating them up over time, and that gives cumulative infection hours. Okay. Time for a break. Okay. You're to be congratulated. That was the toughest session we've had in a long time, and the toughest of the boot camp. But we do now have a model which captures environmental contamination spread to a population and vice versa, shedding. We have it in a way that will report the influence of workplaces, homes, total up things across the population in the form of cumulative totals across the population. So that completes looking at SD and ABM like this, SD within ABMs and ABMs within SD. There's a set of models I've given you that expand on this in more detail in the form of a tripartite model, in the form of other models that illustrate each of these. We're not going to have time to look at those. Yes?
On the output, the x-axis just keeps scrolling along time.
Yeah.
Saying you've got a time of 500. Any way you can get it to stick?
Sure.
You show 0 to 500?
So the question was, this is scrolling along. How do we stop that? You go here, and I find its behavior a little bit of a nuisance with that. But if you scroll down, you could see you can set two things of relevance. The most, it says you can display up to a certain number of samples, and I'll make it as many as we want, and how long do we want it to display for? So I'll say, I want it to display for, maybe 2 years or something like that. I don't know if I can do this in this space. It probably will reject it. But no, it likes it. Okay. Sure. I said here.
Yeah, got that done. Then you went to scale.
And then I scrolled down, and I went to display up to so many latest samples, and then with a time unit of 2 years. Okay. So now this thing will, you know what? That's not very helpful though, because it's showing it on that time frame. So I think actually what we want to do there is set it so it's time window. Yeah. I don't know that we want that for the time window.
I've struggled with this before, not being able to get a fixed scale. stay, so it doesn't, well, that's the vertical scale. On the horizontal scale, it'll stay that whatever the fixed number is.
Yeah, I mean, we could set it to,
But that's the vertical scale.
oh, the vertical scale. Yeah, you're right about that. But, you know, we could set it so that it displays up to, you know, up to 100 days, right? 100 times day. This would display up to 100 days here. Yes.
In this one, did we do 2 and 3 in this last one? The one you have up on the board there?
2 and 3. Yeah. Yeah, this is SD and ABM right here.
Okay.
In the sense that every workplace has a stock and flow model in it, right? So every workplace here has a stock and flow model. So SD is within ABM, within ABM. So we have system dynamics within each agent. And now we just added at the end, we added an example of SD, ABM within SD, in the sense that this is totaling up over agents. This stock and flow here.
Yeah, I didn't understand that part.
So all we're doing is we're totaling up over the entire population by calling the population statistic here. This totals up the number of infective people, and we're integrating it. If you want to see another example of this sort, I would look at the basic health economics model. This one here, where we have these high-level stocks, which are totaling up over the entire population. The life years lived for the population, the costs across the model, etc. And those are summarizing over an entire model by calling statistics. So therefore, here we have system dynamics at the highest level, and it's summarizing over a bunch of agents. Does that make sense? So basically, the system dynamics is going at the high level, maintaining the population-wide totals, the things that don't vary by population member. And it's totaling up over a whole bunch of agents. So here the agents are kind of at a lower level than system dynamics. The model we just built, system dynamics, is within each agent and at a lower level than the agents themselves. This first one, we had system dynamics at the same level as the agents. It was producing the agents. That was the first one. Does that make sense?
Not totally, but I need to keep in a little.
Because
I had an error, so I wasn't following that part that you did. So
oh, I see. Did you get it fixed? Do you want help with? Right. Okay, so let me take a look at